So, one second. Okay. Okay. Um. So let me get started. One second. Okay. So just the setting. So you have a finite set X. Um. You have a bunch of density operators, and you have a PMF on X. Then sigma turns out to be the ensemble average. Clearly, we know sigma tensor n is 1 by, no, 1 by, we know this. What we are looking for is a smaller, the smallest, would say a smaller collection. C sitting inside Xn, that is C is say Xn of 1, Xn of 2, all the way till Xn of capital M, so that if I uniformly pick these guys, so sigma tensor n minus the uniform ensemble average of this ensemble, so m equal to 1 through capital M, rho of xn of m, this falls exponentially. So here what is happening is m is a function of n, so I should be writing mn here really. And as n goes to infinity, so mn increases at some rate as n goes to infinity, and at that rate you will be able to achieve sigma tensor. That's what you're looking for. Okay. Okay. What did we do? So we are going to take a collection. So we take a random collection x. We call this random collection as xn of 1, xn of 2, until xn of capital M. I take this random collection, and so now I have, so the random object is essentially this sigma tensor n. I'm not going to write this subscript n because it's not going to. You should know that. So this is the random object, and if I can show that the expectation over x is say 2 power minus n eta. So clearly, what is happening is this is what's happening. So you're taking a collection. So you take a collection. You take a collection C, and you're evaluating. So what do you do? So given a collection C, let rho C, the very bad notation. So let me use maybe let me say theta C. Theta C is essentially this guy. So my collection is fixed, little xn to little xn m1, and this is my theta C for that collection. So what we are looking at is pick every collection with some probability, and then you look at this sigma tensor n minus theta C. If this is less than 2 power minus n eta, then clearly at least one of these guys should be less than 2 power minus n eta. Otherwise, the average will be more. That's the idea. So this implies there exists a C star for which this is the random coding argument. Just explicitly writing this down. There exists a C star such that sigma, so there exists a C star, let's call it, I'll just put an X. Okay, I'll just put a, I don't want to put a, okay, so let me just do X star n of 1 all the way until xn star of m. So that sigma tensor n minus 1 by 2 power, m rho xn star of m equal to 1 through capital M, this thing is less than 2 power minus n eta. This is what I'm saying. So this we have to just show that this is true. And what is our collection? So if we take a collection xn of, so if I take a collection, so my collection is x 1 of 1, xn of 1. This is the first element in that collection. So I'm just putting a, so this is the first element, x2 of 1 all the way until xn of, x1 of 2 all the way until xn of 2. So this is my second element in that collection, second what we call a code word, right? x1 of m all the way until xn of m. So this is my collection. What is the probability of C? Well, I take so I have this distribution Px. Remember, I started with the distribution Px, right? I mean, I'm really trying to get to the ensemble average of this distribution. but I will choose that px itself. One could be more intelligent, doesn't matter, I don't care. I'm going to choose that same distribution, and I'm going to pick my, so this is, it's all complete product. Every one of them, every one of the symbols that make up the product, I put them together. I just take the whole product. This is the most dumbest distribution to take, but it turns out that's good enough. You can do some non-trivial thing. Okay. Great. So what are we doing? We are doing this. So with this distribution, we are computing the expectation of this object. I mean, it's just amazing. It's just mind-boggling, right? It's just weird, right? Saying that, you're looking for something something non-trivial. You're looking, I mean, the collection of the big set of all collections is a big haystack, and you're looking for a needle in that haystack. But you can just, average and show that the average is good. So, I mean, you don't really have to be smart. You can be just completely dumb. And that works. So this is what I and what I did, I'll just repeat the first few steps I did last time, and then so take the exam seriously. Every step I don't do in the class, I'll ask in the exam. Okay, serious. Okay. Okay. So I argued. So I'm taking. So I took T as so T of C, the random object. This is my random object. And okay, so show, I told you I'm going to write things in red. Show expected, if you take the expectation, so this is a random object. So you take the expectation with respect to this distribution itself. So each term here, you're going to multiply with pxn and sum. I mean, I can literally do it right here. You can show that the expected value of t is sigma tensor n. I mean, I'm going to do this problem, because it's so very tempting for me to do. So expectation of this is 1 by m, linearity of expectation. And if you observe each fellow, if you look at, so this is the distribution of the entire collection. So you can ask, okay, what is the marginal of the second guy? Well, you just sum over all the other guys, and you're essentially going to get the product, right? Just the product of the symbols. So you're going to get something like this. So the probability, so m equal to 1 through m, I'm going to write it as it is. The probability that capital Xn of m takes the value Xn is just, so it's Pxn of Xn times the value when it is Xn. So that's what this is. And you sum over all Xn. Okay. Well, so this is just sigma tensor n. That's all, really. So what we are really looking at, you observe, what we are really looking at is the expected value of t minus expected value of t, where t is the object at the top. This is what we are looking at. So I'm going to, you have to show, okay, so I'm going to define T1 as some other beast. And so let T1 be kind of quoted m equal to 1 through capital M. I'm going to quote it with pi. So pi is actually the unconditional typical projector of sigma. Unconditional, I don't need to be writing this word unconditional, but just to contrast it with the conditional, I'm writing it. Unconditional typical projector of sigma. Remember, there are what are the characters that we have? We have these characters, and we have this. These are the different characters in our play. So I'm going to take pi, the unconditional typical projector of sigma, and you know what pi xn is. So what I'll do is from now on, I'm just going to put a row. I mean, sometimes I'm going to put the row. Oh, maybe. Yeah, let me try and put a row when, I mean, okay, I don't know. Maybe I'll do this. I'll not put a sigma. It'll just, you will just feel intimidated. So I will put pi xn of m. So this is so pi xn for any pi xn is the conditional typical projector of rho xn. This is a different beast, okay? So I'm using the same letter pi. I don't want you to get confused. When there is no subscript or superscript, it is the unconditional typical projector of sigma. When I write pi xn, it is the conditional typical projector of rho xn. Okay. Do this proof yourself at home. Pi xn of m pi. Okay, so I'm going to quote this. I had only the rho xn sitting at the. I put a lot of brothers and sisters to it on the left and the right. Okay, so this is my T1. So I will only show the key term. You will see that the other terms are essentially not hard. So you can do this, right? So let's say, so you can do this, right? Let's say T2 equal to T minus T1, and you kind of show. So you can do this. First, you can do this. Well, you can do, so you can do, okay, so I'll tell you what all you need to do. So you can first do a T1 tilde, so you can write a T1 tilde as, maybe let's see. Okay, I might be bad at this notation. So I'm going to say 1 by m equal to 1 through capital M. Let's say T tilde. I can do T tilde to be this. Rho xn of m indicator function xn of m belongs to T delta n, and I can do a S tilde to be 1 by m equal to 1 through capital M, rho xn of m indicator function xn of m does not belong to T delta n. Clearly T equal to T delta plus S delta. You can show that the S delta, so you're going to get something like this, right? You're going to do a lot of work yourself. It's not, I mean, these are not hard, but you do a lot of steps to come to the critical step. So you're going to write this as expected value of T tilde minus T tilde plus expected value. I'm using triangular inequality when I'm doing this. Minus S tilde. You can show this term is very small because each fellow is a bounded trace, and you can do it linear. You can do the triangular inequality and then just compute the probability of this and show it as small. Okay, all that you can do. And T tilde you can now write it as T1 plus T2, where T1 I'm going to add an indicator function. Actually, you don't need to do this, but I'm just doing it just so that you don't ask me any questions. I can do this. T1 is this. T2 is T tilde minus T1. Okay. So T1 defined above. I mean, really, I don't need to do, but just, if you get some doubts. So this is my T1. And I define T2 as T tilde minus T1. So T tilde is also, you have this indicator function, but it doesn't have this quoting. That's all it doesn't have. So you can show that those terms are not hard. Really, the term that is critical, that that you really need to handle is the following term. So it is going to be, I did this last time. I am just kind of in some sense restating that those terms can be done. So you're really looking at the following. T1 minus T1. You're really looking at this. So I started last time and I'll continue. So this is, so expected value A is trace A dagger A root. So this is root. You know what is the root of an operator? So I'm going to write T. I'm going to just switch the T1 and the expected. I'm going to just do this. T1 dagger T1 minus expected value of T1. Okay. Sorry. What's wrong here? Are you guys there? I haven't heard anything from you so far. So.
Yes.
What's wrong here? Nothing big. You have to put a trace. That's all. Trace. Okay.
Yeah. Yes, sir.
That's all. Okay. Expectation and trace commute. T1 minus expected value of T1 whole dagger. T1 minus expected value of T1. Trace is linear. I will write every step. Okay. Now you are using the, forget the name. So operator square root is operator concave. Square root is operator concave. Not at all a trivial result. So what it means? So that is what does it mean? Suppose lambda is between 0 and 1 is a real number. A is greater than equal to 0, B greater than equal to 0, or PSD. Then P times, sorry, lambda times root A plus 1 minus lambda times root B is lesser than equal to lambda A plus 1 minus lambda times B. See, these operate, I mean, showing something like this is crazy, okay? Because this is some operator with some spectral diagonalization. This is some operator with some other spectral diagonalization, and you have to show, the eigenvalues dominate. It's not easy, but this turns out to be true. And so we will, so we will exchange the root and the expectation. So I'm going to say this. Expectation of T1 minus expected value of T1 dagger, T1 minus expected value of T1. What is T1? T1 is this. 1 by M equal to 1 through capital M, pi xn of M, rho xn of M, pi xn of M, pi, with an indicator function if you desire so. This indicator function is really not needed, but I put it so that you don't have questions later on. I'll just write 1, okay? 1 means, so by definition, the blue 1 means indicator function. I'll just say M. Indicator function xn of M belongs to T delta M. It may not be blue. I might end up writing it in black itself because
I have to keep changing this pen. Okay, so what am I doing? So let's, we can use distributive law in the space of operators. So I can say expected value of T1 dagger T1 minus T1 expected value of T1 minus expected value of T1 whole dagger T1 plus expected value of T1 dagger expected value of T1. Okay. T1 is big, so let me just do this. So let AM be 1 by M, sorry, not 1 by M. Pi, maybe I'll put 1 by M. How does it matter? So 1 by M, I'm just going to name each fellow, so that it's easy for me. Just gets unwieldy. Rho xn of M, pi xn of M, pi. Okay. So what are we looking at? And so we are looking at something like this, right? So focus on operator under the square root. Just going to look at that. So I have expected value summation AM dagger AL minus summation AM. Oh, there is a dagger missing here. AM dagger. Can I say this? Can I say this? Can I say this? So AM bar is expected value of AM. Maybe. What I'll do, can I do, so this is, so what is, okay, so maybe I should do this so that it's comfortable for you. So this is what, this is summation. Just thinking, how do I convince you without too much trouble? So let me say, can I say this? Can I say P of, so this is really what it is, P of xn, P xn of xn, 1 by M pi xn, rho xn, pi xn, pi. This is what it is, right? So I want to give this a simple. Okay, let me define this as, AM bar. Okay. Observe that doesn't depend on AM at all. It doesn't depend on M at all. Okay. But I'll just write it as AM bar. Tell me if you get, I want to ensure that nobody has any doubt. So I'll continue. Tell me if you have any. At any point, if you feel little uncomfortable, tell me. Or if you feel okay, how do you get this step? Just tell me. So AM bar, AM plus AM bar.
Just one question.
Yeah.
When you define this AM bar above,
yeah,
In the summation, it should be px of x and m, right?
Yeah, but see, each one is identically distributed, right? You're right. So you're right. So AM should be actually this, right? So it should be 1 by M summation probability that xn of m, this is the big form, probability that xn of m could do this times pi of pi xn rho xn pi xn pi. Correct? You agree with this?
Yeah, correct. Yeah, that's just by definition of rho sub x and m, right?
Yeah. This
Yeah.
is just by the definition of the expected value of AM.
No, so then it's
Probability
m
that
bar.
capital Xn of m equal to little xn times this whole summation over xn.
Oh, that should be m bar then.
Yeah, you're
AM.
right. AM bar. Sorry.
Okay. Oh, yeah. Okay.
But this distribution is identical for any m. And hence
Yeah.
I can just
Okay.
write it as xn of xn belonging to xn, p xn of xn, right? Because that's what with mth guy is chosen. Every guy, remember, every guy is chosen with the same this thing,
Yeah,
right?
distribution.
It's
Yeah,
just
correct.
so when you want to find the distribution of a particular code word, you marginalize over the other. That means you sum over all the other guys. You sum all of them get knocked off, and this term will be there, but this term will be just that product.
Yeah, got it.
Yeah. So that's why it's invariant with M, really. Okay. So I'll continue. Yeah, please ask, okay? Any step, please ask. I'm just doing this elaborate. I mean, I'm not it would go very fast, but I'm just doing this elaborate. Okay. There's an expectation outside. Okay. So whenever you see AM bar, this guy is sitting there. Okay. Whenever you see AM bar, this guy is sitting there. So this guy is sitting here. This guy is sitting here with the dagger. So it's a dagger, 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 dagger. This guy is sitting here. This guy is sitting here. Okay. Okay. Now, look. Okay. So the first term, right? So first term looks like okay. So I'll continue. Just want to ensure that everybody gets everything. I might go a little bit over time, but I'll ensure that everybody gets all the steps. So we are looking at. I will do a little bit of I had actually written in my notes today morning slightly simpler. Maybe let's see. Just give me 1 second. I'll work this out to make it more easily convincing. Oh, okay. This is not very. Okay, that's fine. You will maybe. Let's see. Yeah, that may be slightly simplifying. Okay, though it's correct. Okay, let me do this. So I'm going to write each term, not a big deal. Just bear with me. The notation is slightly more. So this is this M L A M dagger A L minus
AM. Can I say this? Are you going
to agree with this? So this is this. Give me 1 second. Let me see how do I convince you easier. Okay, how many of you buy this and how many of you don't buy this? Let me see. This is the first term. I'll write it as is. I'm not going to do anything. Minus if you buy this, I don't have to worry, but if you don't buy it, I'll have to show it. So how many of you agree with this? So what I've done, I've inserted the expectation. So I've inserted an expectation here on the second term and an expectation here on the third term. And I claim, so I will write everything and then look at it and tell me if you have a doubt. It's obvious, but because they're operators, you might be always thinking, okay, I have to be careful, I have to be careful. AM dagger AL minus, can I write this? M L AM bar dagger AL bar minus M L AM bar dagger AL bar plus same thing M L. How many of you believe this? So I'll let you look at these 3 steps. So this is what I started. I have this, then I have this. So what did I do in the first step? The second term is anyway just, if you see the second term, right, it's just a bunch of these summations. Actually, you will just get, when you're summing m of them, you will actually get the 1 by m out. You'll actually just get one term. That's really all this is. But just for not making it more confusing than what it is, I'll just write it like that. Now, when you have the expectation on the outside, the randomness is only in this. So you are actually just doing the expectation. That's what I'm doing here. So it's here. Here, there is no expectation. It's constant. It's like just this times this. So that's what it is. So you have this. If you buy this, one of the terms knocks off. So one of the terms knock off. I'm gonna copy paste and write this because later the notes will have it. Copy, paste, it gets knocked off. So I have the following. So I claim I have the following. Expected value 1 by m squared m L pi xn of m rho xn of m pi xn of m pi xn of L rho xn of L pi xn of L pi. So one term here, the other term here. And the 1 by m squared, I'm doing an expectation of the outside. This is the first term. What is the second term? Minus, this is what I have. 1 by m squared m L, right? Expectation of pi xn of m rho xn of m pi xn of m pi times the expected value. So these two are different, okay? There's a one expectation of the whole thing, and the second one is the product of the expectation. They are very different things. Pi xn of L rho xn of L pi xn of L pi. So let's do this. So there are 2 cases, right? So let's keep the second term. Let's so let's look at the first term. So the first term. So this. Okay. How many of you so far? Okay, put a thumbs up. I know you can't reproduce all the steps from the beginning, but at least you don't have any outstanding thing. At any step, if you have a question, just stop. I want to go slow. The proof is different from what is there in the book. You haven't seen this proof, and I just want you to ensure that you get all the steps. Okay. So now there are 2 cases, right? Look at the first term. Can I say the first term is expected value of 1 by m squared, the case when m is equal to L, m equal to 1 through capital M, and here L is equal to M. So, sorry, L is equal to M. Okay, so I'm not going to write it, and I'm just writing it because it's superfluous. I'm just writing it. So it is like this. So tell me xn of m, rho xn of m, pi xn of m, pi xn of m. I'm just writing it so that I'll end up going slowly. If I just do a copy paste, I'll go very fast, and then you will feel a little down. So that's why I'm writing it. In this multiple times, you can slowly see it. Okay. Plus I'm just writing the first term. Now the first term, the cross terms, m equal to 1 through capital M, L not equal to M. Okay. So really, this summation is trivial, but I'm just writing it because I want you to see it. I mean, there's no summation there. What is this? This is pi xn of m, rho xn of m, pi xn of m, pi. How come I'm not writing? Okay, there are two pi's here. I didn't write the 2 pi's in the middle. Pi. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Pi xn of L, rho xn of L, pi xn of L, pi. Okay, so this is an expectation. Observe that xn in m is not equal to L, m is not equal to L implies xn of m and xn of L are independent. That means what? That means that probability that xn of m equal to xn and xn of L equal to, let's say, x tilde n factorizes as a product. It is very important, extremely important in all of probability theory. Independence. So this factor. So this is just p xn of xn times p xn of x tilde n. Okay, sorry, there is no tilde. Okay. So when I do the expectation of this, right, I will sum over an xn and an x tilde n. So I'm going to get something like this. So what is the so let me write the first term as is, because that's a more sensitive term. I'll come to it at a later point, but I'll show you the second term will also vanish now. M equal to 1 through capital M. Now I'm going to copy paste. Okay, it's too big. I have to write this whole thing once again, which is this thing. I'll write this whole thing once again. Copy. Paste. I have this. Look at the second term. Second term looks something like this. Plus 1 by m squared. Can I say it is m equal to 1 through m, L not equal to m, right? Now what I will do, I will, okay, so I'll write it and then I will show it to you. So there will be an xn and there will be an x tilde n. Really, I want an xn of m and an x tilde of L, but really it doesn't matter because, it's essentially the same thing. Okay. If you really want to do, try and do this and see that there's not going to be any change. So you'll get p xn of xn times p xn of x tilde n pi xn, rho xn, pi xn, pi x tilde n, rho x tilde n, pi x tilde n, pi. So what have I done? I have computed the expectation of this times the expectation of this, because essentially it's a product. So when I write what is the probability that it is these two, you'll get pxn times px tilde n. So you just pull these guys separately and then just do the summation. That's all I've done here. Okay. So what is this? This is essentially, I claim this. I'm looking at the second term. Okay, I'm looking at the second term. Oh, I wrote the first term. Okay, so this is this minus this. Okay, so maybe before I proceed, I'll go back and kind of recollect what all we've done, so that you see what's going on. Just as kind of a big level. So you started with this. You're looking only at T1. You will somehow show that T1 and T1 is the critical term. Okay. You first split T into T tilde S tilde. T tilde S tilde doesn't have the indicator function. T tilde has the indicator function. And now you again split T tilde as T1 plus T2, where T1 has all these brothers and sisters sitting aside it, and the T2 is T minus T1, and I kind of showed you. I kind of showed you without proof, which you will the rest of the things you'll do in the exam. So I just showed you this is the most important term. So let's start looking at it. So I looked at the trace of the root. Now expectation and trace commute. So the expectation goes inside and the trace goes outside. Now I use the operator concavity, and I said, okay, I can get the expectation inside. Now I'm just enlarging this thing. Now I'm not doing anything special. I'm just enlarging and evaluating each term. So first, what did I do? I wrote the entire distributed law and just wrote the entire all four terms. I applied the expectation on the term that did not have the expectation. So here this is a constant. So expectation of a lambda times a random variable is lambda times the expectation of that random variable. Okay, that's all I've done. So this is kind of constant because our expectation has already been taken out. There's no randomness there. So I apply the expectation here. So that's really what I get here. Okay, so I start with this and I end up here. So in the first place there are no bars here and here, and when I apply the expectation, the bars come in. The bars come in here and here, and then I observe that I'm doing the last three terms are identical with two minuses and one plus. So one of the plus goes away, one of the plus and the minus go away. So I'll just have this minus this. That's where I've come until here. Now what I'm doing is I will try and show you that. Okay, so then what I do, I look at the first term. There is a summation over m and l. There are two cases. So I write the first term, I write the second term. First term, there are two cases. When l equal to m, the summation actually, the second summation squishes out. So I'm pulling out that l equal to m case out, and the l not equal to m. Okay, and the l equal to m case, I'll go later. I told you it's a sensitive term, so we'll look at it later. Now let's look at the l not equal to m term, and I just evaluated the expectation. That's all I've done here. Now I claim, so this is, I'm only looking at the, so this is only the, okay, so this is only the first term. So let me run, yeah, oh, this is only the first term. Yeah, I said this is the sensitive term. So I started looking at the first term. That's what, okay, hold on. So let's call this big alpha. Let's call this big beta. So this is alpha. Okay, so alpha has two terms. I'm getting alpha as this, right? What is beta? So I claim, now before going further, alpha first term as is, copy, paste, minus, I claim, this is the second term, right? The second term I claim is the following. It's 1 by m squared, m equal to 1 through capital M, L not equal to M. I claim it is AM bar, AL bar. Dagger, maybe with a dagger. I don't know, dagger maybe put the first time. That's all that is, right? Because I can really split this x tilde n on this side and x tilde n on that side. And really, okay, I should not put the 1 by m squared. I should just put, so I can, so let me actually explicitly show it. Copy,
paste. So can I say this is by M here and by another M here. So this I claim is just and I claim so I'm going to do this one more. It's okay. I'm going a little repeating some steps in some unorderly fashion, but it's okay. It just gives you some time to see. Copy, paste. Okay. Second term I claim. So this is again. So second time I simplify now, and I'm going to say, can I say this is? Yeah, I want to do this. Okay, so that means I can write. So the second term is identical to. So now I claim this thing.
Just one thing.
Yeah, just one second. Let me write this down and then I'll show you the entire thing. One second. So I claim this is the following. I claim this is M L not equal to M. Oh, this is plus. L not equal to M. A M bar dagger A L bar. Yeah, tell me what's your question.
That no, I think when you moved it inside, even the P, X, and tilde should move. But I think you right when you put the
You're right.
summation-
You're right. Good point. Thank you. Good point.
Yeah, but we have it there inside. Yeah, now it's correct. Yeah.
And this guy has to come here. I can do all this as long as I don't, upset the operators by moving them one in front of the other. I mean, you can't shift the relative positions of the operators. The operators will get unhappy. Is it okay so far?
Yeah.
So just recall. So we have. So I got rid of two terms. I have one term on the left. The alpha minus beta. Okay, and this alpha term, I split the summation into L equal to M and L not equal to M, and I get this. So I'm working with my alpha, the addition. Now look at what is beta. What is beta? Beta is actually this. Beta is actually this. Because of independence, right? Because of this property of independence, I'll just write down here. Beta is M L A M bar A L bar. So it has an extra term actually. For every value of M, there is an extra L. There is one another term. The equal term is also there here. So alpha minus. So if I look at so essentially, what am I looking at? I'm looking at alpha minus beta. So alpha minus beta is something like this. So alpha minus beta is expected value of the sensitive term where there is no independence. The whole point is there is no independence in the first term. It's both the same random variable. It's both xn of m, xn of m. That's why I can't do what I did in the second term. That's why I'm going to deal with it carefully. It's actually a beautiful analysis. So I mean, yeah. So this is pi xn of m, rho xn of m, pi xn of m, pi. That's the first term. Plus, I have this, right? M L not equal to M, A M bar dagger, A L bar minus
No matter what the M and L is, you get this. This is what your L bar. Now, so what do you have? You have something like this. So can I say alpha minus beta is, I'm not going to write the first term again. Just going to copy. Oh my God. Paste minus, you have the following, right? When M bar dagger AM, because here you're adding on every term other than L equal to M, you're adding those terms also. So L not equal to M, it'll get cancelled, and only when L equal to M it will survive with a minus sign. So this is what it is. Okay. Now clearly this guy AM bar dagger AM is positive semi-definite, obviously, because it's A dagger A is always positive, and you add them, they're all positive. So that means alpha minus beta can only get larger if I discard the positive semi-definite term, the negative positive semi-definite term, that is with a negative sign. So I'm going to get this 1 by M squared. This is the important term, and I'll write it a little bit neatly. Pi xn of M, rho xn of M, pi xn of M, pi, oh my God, it's so big. Pi xn of M, rho xn of M, pi xn of M, pi. Okay, what is this? Let's do this. So remember, what is alpha minus beta? This is what remains after you do under the root sign. Under the root sign, it's a big story. Under the root sign, you showed that the last three terms are identical with two negatives and one positive. So you discarded that. There's only one term, and then you showed that the second term of the first term is larger than this beta term. That's what you showed. So you end up with just at the last, you end up with this. So we have, just so that you don't forget that what we are working with this alpha minus beta. This is what we are working with. Okay. Okay. Let's do this. So let's look at alpha minus. We're not very far. We're almost done. So I claim this is the following, right? So this guy, I'll go neatly from here on. Hopefully, at least for 2 lines. Let's see. 1 by M squared. M equal to 1 through capital M. I'm doing the expectation of this beast, right? So just summation over all xn, P of xn, I mean it's P xn of xn, pi xn, rho xn, pi xn, pi xn, rho xn, pi xn, pi. 10 operators, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, great. This is what it is. This is the final thing. This is the holy grail. Okay. So there are 1, 2, 3, 4 operators sitting exactly its mirror image sitting here. So that means I claim the following. So each step should now be okay, straightforward. M squared. P xn of xn. So don't lose track now. It's important. Because these are the steps that will give you the final thing. So can I say the following? So I replace this pi squared with a pi and a pi with an I. And I put it in the middle. So since it's in the middle, it works. So S A S dagger is less than equal to S B S dagger if A is less than B. And in my case, I've chosen my A to be pi square, which is equal to pi, and my B to be I, which is the identity is always better larger than the projection. That's what I mean. So I've replaced this with an I. I can go.
I can go. What do you know about pi xn?
Now we still have a lot of. So I got rid of one operator. I mean two operators. It's now come down to 8. Okay. Do you agree with this? And if so, tell me why. If not, tell me why.
So what did I do?
I write down the line so that it's clear to you.
So just to trace, this pi
Comes here. This pi comes here. This row xn, I remove a row, half row xn out. This pi is as is. From the right again, this pi is as is. This pi xn is as is. I took out a row half xn again from the right and a row half xn to the left, and I put it in the middle. Is this okay?
Yeah.
Why?
Rho xn commutes with pi xn.
Yeah, it's critical. Pi xn and rho xn commute.
should be now clear why I
Did
did
this. So can I now say this is less than 1 by m squared, m equal to 1 through capital M, xn, p xn of xn. So I'm going to write, so I think, you know what I should do? I should call these guys some names, otherwise it's hard.
So 1, 2,
2, 3, 4, 5, 6, 7, 8. Right now you have 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't know how you get it. I think okay, whatever. I think it's okay, right? Yeah, it's okay. So now I claim this 4, 5, 6 guys, right? I can reduce that. Pi. So pi 1 is as is, 2 is as is, 3 is as is. 4, 5, 6, I claim it is at most pi xn with a 2 power minus n this quantity.
this is the conditional typicality
Result. Remember, I told you there is one indicator function xn. If xn is not typical, all these pi xn's are zeros, so you don't really have to worry. You can go back to our typicality result and check that if xn is not typical, then pi xn is 0. Okay, you can go check this. Otherwise, you don't have to worry. I have put an indicator function that is still there. Okay, so I claim 4, 5, 6 reduces to the following: pi xn, and then 4, 5, 6. 4, 5, 6 just becomes one term, and then I have the row xn to the power half on the left. On the right, 7, 8, 9 is as is. So just to correspond with the above, 1, 2, 3 is as is. 4, 5, 6 becomes one term, and then you have 7, 8, 9 again. and this one term, this is this, and this exponent sitting out. So I'm using conditional, conditional quantum typicality. The fact that the projectors are this guy, when you chop it off outside the conditional typical subspace, inside that they're all tightly constrained. With a minus delta or something, minus 2 delta or something of this sort. Okay. I want to, yeah. Okay. Now what do you do? Okay, I worked this out today morning. Let's see. There's one. Okay, cool. So, okay, I claim. Can I do this? Copy. This is now it's done. Actually, the problem is done. Okay. Can I put an I at the middle? It's okay, right? You will permit me do that. Great. No big deal. Get rid of the I, just collate the terms. Nothing big. Now what? Actually, I don't want to do this. I don't want to do this. It'll just, actually, I don't want to do this. Sorry. I'll just go around and round. I'll do the following. Give me 1 second. Yeah, I will actually do this. Okay, I won't even do this. Sorry about this. Okay. I can go with the next step also, but it's just going to go round and round. Very sorry about this. So you agreed till here, where what did I do? I just use the conditional typical thing. Now what I'll do, I will, can I say this? I'm going to, you agree with this? So what did I do? I interchanged 2 and 3. So I interchanged 2 and 3. I interchanged 7 and 8. That's all I did. And they are again pi xn and rho xn commute. So let me erase these. Sorry. It's like this. Okay. Now I'll get rid of the pi. Okay. I don't want those guys. Their job is done. Hopefully. So 1 is as is, 3 is as is, 2, the middle pi and the 8, I'm going to knock it off. And I'm just going to say rho xn power half pi. Okay. So essentially, I'm putting a big I here. Pi xn equal to pi xn is less than equal to I. That's all. Their job is done. I have a 2 power minus n sitting. I shouldn't forget that. So I'm going to write that here. So 2 power minus n a p x of a s of rho a with a eta. Okay, I'm not writing the eta. That's sitting on the numerator. So I'm going to write this a little bit neatly now because we are getting close. So 2 power minus n times px of a s of rho a. I'm just using a dummy variable a minus some 2 delta whole divided by m squared. I have an m sitting. Hopefully that one m will go. Xn p xn of xn pi. I collate the half, the root xn to the power half and xn to the power half. I have this. Okay. Now you know what we do, right? Now you should know what we do. Minus px of a s of rho a minus 2 delta with an m squared, m equal to 1 through capital M. Scalar is very movable, is a very flexible guy. So I can say this pxn of xn rho xn pi, right? Obviously I need that, right? Because this pi is the unconditional typical projector of sigma. It's not going to do anything with this rho xn. They're gonna fight with each other. So I need good guys to come together. So 2 power minus n times a px of a s of rho a minus 2 delta divided by m squared summation m equal to 1 through capital M pi sigma tensor n pi. Now in good, great shape. Look at how many we got rid of 10 projectors and we are ending up with what we need. Okay, great. Now we are in good shape again. So this is 2 power minus n times a px of a s of rho a minus 2 delta by m squared. Can I say this is at most 2 power minus n times s of sigma plus 2 minus 2 delta pi. Okay, pi sigma tensor n pi is at most 2 power minus n s of sigma pi. Okay, this is a conditional, again, unconditional typicality. Great. So what have we ended up with? So we have ended up with 2 power
summation
huh?
over n, right?
Yeah.
There is a
Thank
summation.
you. Awesome. You're awake. I thought I was the only one doing this. Okay, so what do we have? We have 2 power minus n times a px of a s of rho a minus 2 delta. I'm going to pull the other guy also, s of sigma minus 2 delta. I can get rid of one of the m squared, right? Because the term doesn't depend on m at all. Okay, divided by capital M to the power 1, just to emphasize. There is no I think there's only pi. Okay, so this is so alpha minus beta is lesser than this quantity. Copy. Paste. Okay, let's go back, rewind our story. I'll pause for a minute. Maybe I'll just kind of tell you all that we did. Not a really big deal. Okay, we started with this. This is the first term. The second term got knocked out. We started with this. So both the xn's are the same. So we do the averaging. We put the xn and then we sum. So you have this little xn's and then you have the sum. So I'll go step by step. I'll just kind of. Okay. First, the middle guy, get rid of it. There are too many guys outside. You don't have to worry about the guys in the middle. You can get rid of them. So you get rid of that. Okay, that's the first step. We came here. Then, so you get rid of that. You just write it as is. I've just written it multiple times, so it looks big. That's all. So you have the situation where you have 8 projectors. You have 2 have gone. Okay, then you get the row. You get half from the left and half from the right. And you put that in the middle. And the commute, you can do it. You put that in the middle. There may be simpler ways. This is what I thought of. You put the pi xn rho xn in the middle, and then you can get a bound. So you can bound. You can this whole 4 pi 6 term you replace with this term with only 1 pi. Okay. Then you get rid of all the pi's. You don't need that. So there is a pi here and there's a pi here. Pull them in the middle. Get rid of them. It's not really too hard. So then you collect the half root xn's remaining. So you have this, and get rid of the pi's, put the I, then you have a pxn. Now you just, you are now sitting with pi xn's have all vanished. So now you better try and get your sigma tensor n, because pi only is happy with sigma tensor n. So you sum over the xn's, rho xn, pxn, you do the averaging, you get sigma tensor n. Then finally you get rid of the pi, the sigma also, sigma tensor n, and you get this. You get 2 power minus n times this times pi. Okay, you ended up with this. That's all. Very simple. Okay. Now, why all this? Why all this? Because, see, I'm after this alpha minus beta root. If I have a root of some, a, b, I'm gone. I can't do anything. It's just, I can't just do anything if I have a root a, b. But now what
Sorry,
do I
can you
have?
just, can you just go back to the beta part? Can you just show me what beta was?
Yeah, I'll show you what beta was. So we'll go back. Read. You can't read the Ramayana from the half. So remember, you had 4 terms, right? You had 4. I'll tell you. So I'll quickly tell you. So the expectation came inside the square root. We started from here. Okay, we'll go very quickly. Started from here. Expectation of the trace of the norm, root of dagger. Okay, we started from here. Expectation and trace commute. Expectation comes inside. Then you start evaluating. So we observed that these term, this term, and these 3 terms are identical with 2 negatives and 1 positive. So that's what this whole mess. So so these 3 terms are identical with 2 negatives and 1 positive. So only 1 term will survive. That's what we came here. After this was our alpha beta. So this was our alpha. So it's the first term, and this is the second term, beta. So here the sum is over m and l. Here you have an expectation of this product, but when m is not equal to l, this becomes equal to the second term. That's what I showed. So alpha part is the sensitive part I told you. So this is the sensitive part.
Oh yeah.
So
when
this
m is
part,
not equal to the independence, use the
yeah,
independence.
when it is in, yeah, when you take 2 cases, the case when m equal to l, this summation is vacuous, and when m is not equal to l, when m is not equal to l, it cancels with the beta. This is your beta. So you have expectation times expectation. When the terms m and l are not equal, it's essentially the same. So that's why the beta term gets knocked off. So you have, so that's really what I did here. This is the first term, sensitive term, m equal to m not equal to l term. This is the m equal to l term. This is the m not equal to l term. When m is not equal to l, it cancels off with the beta. Comfortable?
Yeah, okay. Got it.
So that's your beta. It cancels off. This is exactly what's happening. This is your canceling term. So, and then you have only 1 term, and then I sat with it, and actually it doesn't cancel. There's a negative term here which I remove. I mean, I'm getting over bounded. Doesn't matter. Getting over bounded here. So this is positive semi-definite. So I say alpha minus beta is less than this, and then I do all this. And remember, where is alpha minus beta? Alpha minus beta is coming from this expectation. Okay, and that expectation is sitting inside the root. We've got the root, we had started with the expectation outside the root, but then with the operator concavity, we did all this. Remember, one point you have to keep in note, which possibly you didn't, maybe I didn't explicitly say. See, I took the term under the root and I'm bounding that above and above and above, right? So I'm saying this term is smaller than something else, I'm going to analyze that. That term is smaller than something else, I'm going to analyze that. We are banking on the fact that the square root is operator monotone. Okay, this is one important point. I stated it last time. So operator square root is operator monotone. So if a is less than b, and both are, so suppose 0 is less than equal to a is less than equal to b as operator, then root a is less than root b. This is not obvious. Okay. It's obvious for real numbers, but it's not obvious for operators because well, the spectral decomposition is the same. We need to do something. I mean, this may be not that hard to prove. Anyway, so square root is operator monotone. I'm using that through and through. So that's why I look under the root and just keep on bounding upward above. So I discard this. I discard this, second term, that bar term, and all that. So I'm really using all that. Yeah, this thing. See, I discarded this, right? I kind of discarded this, and I said that I get a higher term, but that higher term should be higher term after taking the square root, and that's using the operator monotonicity of the square root function. Okay, so now why is the story going in this direction? Because I have a root. Okay, so when I have a root, I can't have this alpha minus beta can't be a times b, then I'll be in trouble. I don't know how to evaluate it. But now what we have ended up with is this, right? So we have ended up with this inequality is less than root of this guy. It's really a very, very, very comfortable and satisfying feeling to take the square root of a projector times a scalar. That's the whole damn thing. Okay, so then I know what this is. This is 2 power minus n by 2 times this whole thing. I'm going to write it as 2 power nr. Okay, so this is something like divided by root 2 power nr. That's what it is. Okay, r. So I have 2 power nr number of code words. That's what really I'm after. Times pi. So root pi is pi. Key point. Okay, so now I am in a good shape. And remember, what were we after? We were after trace of root of expectation of T1 minus T1. Remember, this was what we were after. Dagger, T1 minus expected value of T1. This was what we were after. And so now we have just completed the root. So now we have to do the trace. Okay. So trace of, I'm going to write this thing slightly differently. 2 power minus n by 2 a p x of a s of rho a plus, not plus, yeah, plus s of rho minus 4 delta, right? So I'm just copying, okay? So to ensure that I just copy this plus, copy this plus, this minus, and the n by 2. Okay, I have a by r by 2. So remember this, the term at the bottom is 2 power n r by 2. So I can write it to the top with a minus r, right? So I'm going to put a, writing this in blue, minus r.
Sir, S of sigma.
Huh?
S of sigma, right?
Yeah, you're right. Thank you. S of sigma. You're right. Perfect. Awesome. Everybody's awake. Okay. So what is trace pi? What is pi?
It's the size of the unconditional typical set.
Yeah. So this pi is the unconditional typical projector of sigma. So I claim I get this. So trace, the scalar comes out. So we have got rid of all the operators. And we are just getting one exponent now. It's amazing. A, p x of A, s of rho A, plus s of sigma, minus 4 delta, minus r, trace of pi, trace pi is 2 power n s of sigma, correct? So when I have an n by 2 sitting here, I should write this as minus, because there is a minus here. Carefully think about it, okay? There's a minus here, and there is a plus here. So this has to be minus 2 s of sigma. Do you agree?
Yes.
Because this 2 and this 2 get cancelled and I'll have just S of rho. And this minus and this minus, I'll have an S of rho plus. That's what trace of pi is. Trace of pi is exponentially blowing. So what do I get? So I'm going to write this neater, because this is really what we're after at the end of the day. Now we should not forget what we are after. So minus n by 2 A P x of A S of rho A minus S of rho minus R minus 4 delta. Agree? So should be, oh, this is sigma.
Sigma is same as rho.
This is sigma. But wait, there seems to be some, I should be getting R. So, yeah. So R has to be, if this has to fall, so what should I get? I should get, let's see.
Sigma is same as rho, right? Just
Yeah, sigma, I mean, I'm calling the summation as rho, right? I'm calling this Px of x, rho x as sigma. This is my sigma.
okay.
This has to be positive. No, there is some error. Wait. Minus. Hold on. Okay. My xn. Did we get these exponents correctly? Pi xn, rho xn, pi xn, that's 2 power minus n minus, yes, plus by n squared. The n goes. Okay, let's see. So what are we getting? We should get this to be positive, which means R is lesser than. Oh, sorry. I don't know why you didn't tell me. So the M is sitting at the bottom, right? So when it goes to the top, it becomes negative, which means it has to be positive. See, here, see, this is 2 power, so this is, at the top, it is 2 power minus nr by 2, right? So this has to be positive. That's why I was wondering what's going on. Okay? Clear?
Yes, sir.
Yeah.
See, the R is sitting at the bottom. The root M, the M is sitting at the bottom. When it goes up, it becomes 2 power minus n R by 2. So when I have a minus at the minus n by 2 times R, it's not going to be minus R. So now we got it. So this, so which means R has to be greater than S of sigma minus A Px of A S of rho A minus 4 delta, plus 4 delta, sorry, plus 4 delta. And your delta can be arbitrarily small. So if you take so many code words, then you're done. So you're trying to simulate sigma tensor n. Remember what? Sorry, I know you're thinking of sigma. Sigma is our rho or sigma. This is what we are trying to simulate, right? We know this is equal to summation Px of n xn s of rho xn. Sorry, we know this. So yesterday the suggestion was, Niranjan's suggestion was, let's take 2 power n h of x number of sequences. Here we are getting, if you observe, something quite different. So what is this? So you can actually check. This is, yeah. How do I compare with h of x? I'll compare this with h of x.
Yeah.
Let's subtract h of x here. Actually, you can show, I claim this is, okay, so let's see. Yeah, observe that if all the row x's were, suppose all the row x's were orthogonal. Suppose all the row x's were orthogonal. What would be S of sigma? So think of this, and okay, I will leave this as an exercise to show. Suppose you look at this. What is the entropy of this guy? The entropy of this guy is okay, I will kind of leave it to you to show. Use this. Show that when all the row x's are orthogonal, you can show that this h of x is going to be equal to this. Equal. We'll call this theta AB. Just give me 1 second. I actually said that I was supposed to meet a person and I got late. Just give me 1 second. If you call, because I am able to compare this. Okay. See, if you call this theta AB, right? Observe theta B is sigma. And observe that theta A is distribution Px. Okay. And if you use, so what is, and observe that S of theta AB, this is from our entropy chapter, okay? S of theta AB will be the following, right? Will be, yeah, it will be h of Px plus summation Px S of rho x. This is theta AB. And S of theta A is h of Px. H of Px. And S of theta B is equal to S of sigma. And we use the fact that S of theta A plus S of theta B is greater than S of theta AB, but this only tells us something. Okay. I want to try and show that in general, h of the distribution Px is strictly larger than S of sigma minus Px of x S of rho x. I think we had this as convexity. Remember, we had one theorem in the class which said something like this.
Was there equality there?
See,
Yeah,
if
S of
you
sigma
if you
equal to-
Substitute here, you will get S of sigma to be greater than equal to Px of x, S of rho x. This is what you will show. If you substitute this, you will get this. But I was interested in trying to show that h of Px somehow, how does it relate with how is this related with S of sigma minus Px of x, S of rho x? This is what I wanted to show. I actually wanted to show this. I conjecture it as this. And I think there is a way to show this. So this is there in yeah, this is I did one proof in my entropy where I showed I think this is what I showed. I showed Px sigma x is
yeah, this is the equality.
I showed actually. I actually showed this. Can we decipher from this? I showed this in the class in one of the entropy.
Yes, sir.
Yeah,
Yeah.
I showed this. So this proves it, right? So
Yeah.
look at this.
If you look at this, you see that S of sigma minus Px of A, S of rho A is less than equal to H of Px. And this equality holds if all the rho x's are orthogonal.
That also we showed. When
All the rho x's are orthogonal, then we showed that S of summation Px rho x is indeed equal to H of Px plus Px of A, S of rho A. So if they're not orthogonal, it turns out there is a strict inequality. And hence, you don't need H of Px number of code words. Is this convincing?
Yes, sir.
so we have shown this. So the covering lemma says
So I didn't, okay, I want to say a little bit more on the intuition. So, I've gone really over time and I had actually a meeting scheduled. So can we, so I will, next class, after class, I'll kind of do an interpretation of this covering lemma. And then after that, I will do a application of covering lemma. So we have, the proof is complete modulo the initial steps, the T1 and the T tilde business. Okay. I will possibly, I can do those steps. Those steps are actually there in Wild. So if you look at Wild also does the same thing, but the key term, right? The key term that is this, the T1 term, this whole analysis, he doesn't do any of this analysis. But from the T to T1, he has got some sequence of steps. You can just follow that. But the T1 analysis, he uses what is called the Alswede-Winter operator inequality, which is also, it's a powerful tool, but it has some constraints with that tool. You can't use it everywhere. And I am going around that in a completely different way. So take a look at Wild. Wild will actually take you, Wild will actually give a sequence of steps taking you from here to here. I'm going to ask that in the exam. Okay. So And from here, I give you a different analysis. And this is really the key term. I mean, the real interest really is in this term. So I give you a different analysis, and we have come up with the rate. Hopefully, all the steps are, I've gone through it so slowly that I think, I know you can't put the pieces together. For me, it's very natural because I did this myself. So look at it. Next class, I'm going to give you a little bit of interpretation of the covering lemma and the packing lemma, and I put them in perspective. See that you get the same rates in the packing lemma. If R is less than this, you can transmit over the CQ channel. When R is greater than that, you're covering the space. So it's very interesting. This is a phase transition. And I will talk about that in the next class initially, and then I'll go on to its. I'll give some space for some doubts and things like that. Okay, so that's the end of the class. I'm going to stop recording. Okay, are there any questions? Oh, there are 2 chats.
Yeah. Okay.
Can you just go to the red part which you had shown before? Just scroll up a little bit. Expectation of that thing. I think it's above this part. No, still above this.
That's all.
Yeah, this part.
Yeah.
Oh, slightly below this. Yeah. This part where you have the probability, should that once more be xn of m in the second last red line which you have there? Expectation.
Here.
Yeah.
Here, this is okay, right?
That is fine. You're just taking the expectation inside.
Now I'm doing the expectation. So this guy that you see, this blue guy that I delineate now, is the expectation of this blue guy. Because, so what is expectation? Take one realization, multiply with the probability. Take another realization, multiply with the probability, and then add it. That's what I'm doing here. Take one realization, xn, multiply with the probability, and add over all xn.
Okay, no, I got that. But should there be a xn bracket m? That's what I'm wondering.
There should be, but they're all identical, right?
Oh, they're identical. Okay,
Right.
so you're just ignoring. Okay.
Yeah. So what will happen? I'll tell you. There will be an m here, and there will be an m here. This xn of m, now we are just xn of m is a dummy variable. Is a variable of summation, right? So okay,
Yeah.
maybe I'll do it. I know what you're doing. So let me do this at the end so that you feel happy to sleep at night. So I'm looking at this.
Okay. Let's look at one term. A generic cap. What is this? Do you agree it is just this? Right?
Yeah.
So, I mean, you can write, and if you
Want to put, you can write an m here and an m here, but you're just calling the dummy variable differently.
Yeah, correct.
So really this is just 1 by m. If the whole point is, if this distribution was depending on the xn of m, then you have some interesting things. That's not happening.
Oh.
So you have simply, the same guy keeps on coming. The same product summations keeps on coming.
Each of the x and m's are equal lightly, so m equal to 1, 2, 3.
Yeah, identically distributed, because you're simply, each fellow is identically according to pxn.
Yeah.
The dumbest distribution to take. I mean, you feel that, somehow these code words, they have to have some internal structure, in the sense, one is this, the other should be this, one is this, the other should be this. So you want to, if you pick this to be this, you should pick that to be that. You feel like that, but turns out it's just, just random. I mean, just identically distributed, irrespective of where they sit, you just pick that, and you don't care about what you picked previously also.
So you just run over all the xn's which you have and take the probability of them and multiply by rows of xn.
Yeah.
That's how you get the expectation.
Yeah.
Yeah, correct. Yeah, because x and m can take all of these with the same probability.
Yes.
So it's the same thing. Correct.
Yes. It's like you call it A, and you're picking with you're picking 0 with probability P, and 1 with probability 1 minus P, or whether you call it the 0th code word or the first code word, if the distribution is the same, the averaging is going to be the same.
Yeah.
That's why all these guys are the same beast, and when you average again over 1m, you just knocks off.
Yeah. Okay. Got it.
I can, sit with some of you. I mean, if you have some doubts, I can sit with you and, kind of ensure that you get every step. We can do a little bit of, next session I'll do a little, I mean, I wasn't fast today, but next session I'll kind of, give you some intuition and tell you what's going on. I mean, there is this, that's why this quantity, this, as you saw, right? This quantity, right, which is S of sigma, S of summation px minus summation px s of, I mean, the summation is sitting inside here and the summation is sitting outside here. This quantity you observe, it was the capacity of the CQ channel. So when R is less than that, you can get disjoint, guys. When R is little more than that, they're overlapping, but not that they are just overlapping, they are completely covering the entire space in as though it is sigma. So you've essentially simulated sigma. I will actually, last time I did some cloud covering and all that, right? I'll build on that intuition more clearly. I wish I could do it today. I was thinking that I'll finish this proof quickly and then I will do that, but this proof I went a little slow. Okay, so I want to hold a class either tomorrow or Monday at a convenient time. So I'll send out an email, or if you guys, there are some times that don't work, let me know. I should try to do it maybe tomorrow around this time, maybe one on Monday or something of that sort.
Monday again GCP.
Okay.
At 3:30, I think so. This time it's at 3:30 to 5, but then I'm free after 5.
Okay, I might do it either tomorrow evening or Monday morning then.
Yeah, tomorrow I'm completely free.
Yeah, I hope this lecture is sufficient. Was in a way so that all of you don't go back and have to do a lot of reading. It's not. I mean, I went through the proof steps. Essentially, it's kind of the same thing. Obviously, you should look through it. I have this even teched up. If you want, I can put it in the. I have this teched up, so I can put it in the repository. Okay, cool. See you then.
Sir.
Tell me, maybe.
Sir, regarding the exams, like I wanted to know what is the format of it. Like
format will be you have to go through everything. So what I will do.
Like, will it be like the normal exam, like writing exam?
Huh?
Will it be like the normal exam we give?
I will. So okay, you're asking about the exam. Little early. What I'll tell you is the following. See, I'll finish classes early. This is my plan. I'll finish the classes early. I mean, maybe in this week. I'll give you a time to kind of go through the material. And I will also sit with you and help you with all your doubts through the material. And then we'll have the exam. The exam will be, I want you to work out all the steps that's done in the class. It need not be like, I want you to be comfortable with all the, kind of the arguments here and there and here and there and some holes which I left. I want you to be able to fill up. The reason I do this is the following. See, if you go back today, right, and you look at the covering lemma, I did, some of the terms I didn't do the analysis. If you do the analysis, what you will do is you'll go back and use gentle measurement lemma, you will use measurement between closed states. And when you go there, you will see the trace distance and all of that. So the idea is that by filling all these gaps, you actually become comfortable with all the materials. If you see, the material has been literally coming on top of each other. Every step, right? You start, okay, it starts from the distance measures, then you have the entropy chapter, then you have typicality chapter. And really, we are doing all applications of these tools. And every proof step will involve some of them. So it will be a mix of use of these tools. Like, for example, right, if you go back to in Wild, if you go back to this measurement on closed states, I did one lemma. I proved the measurement on closed states, using that supremum thing I showed. But then there is an exercise 9.1.8 which I gave you for homework. That is where, when it's not a state, you actually prove it. And we use that in some of the proofs. So I want you to be comfortable with the entire material. You don't have to, so that's essentially it. I'll tell you more in the next few days. Don't worry.
Yes, sir. But so like you will have to write it and send it to
I will.
the normal format.
No. I will maybe ask somebody to proctor the exam. I don't think I'll do a take home per se, but I'll give you more time. Something of that sort. That's what I'm thinking.
Yeah. Yeah. Okay.
Yeah. Okay. Cool. I have another.
So for the
exam
itself, like, will you be expected to recreate any proofs, or like, will we have questions like the assignments that we just have to use whatever we have done to like prove more things?
It will be a mix of both. I mean, I'm not going to give everything very new because that's going to be hard. At the same time, I'm not going to give everything that's there in the book because that's going to be too easy. So it's going to be a mix of the two.
All right.
And will it be open book or closed book? Like in the exam hall, can we look at the previous results or?
I'm okay making it open book because again, I'm not going to be asking straight from the book, and possibly I'll be asking some things even the book doesn't have.
Just to refer to the results would be helpful to solve a question.
Yeah, but at the same time, I'm okay making it open book. I have no problem with that, but I don't think. I'm okay with that. Yeah, we look at it. I'm okay with that. Maybe, but then by putting in some things that are there in the book, I can make it easy for you. But then if I give you the book, that opens the thing. So I'll have to think about it a little bit.
Okay.
Yeah.
Okay.
Good. I have to really run. We'll meet on the exam. Not a big deal.
Yeah.
Okay. Stop recording.